All right, today we're going to tackle a huge challenge in computer engineering. How do we make our programs way faster and handle just enormous amounts of data? We're going to break down the core strategies for scaling computation, all the way from making one machine work harder with multithreading to coordinating a whole army of computers with distributed algorithms. Okay, let's dive right in. So, to get our heads around this, let's start with a problem, a really big one. Imagine you're in charge of academic integrity for a massive university. How in the world do you find one single copied sentence that's hidden somewhere inside a million different essays? I mean, scanning that by hand? No way, it's impossible. This is exactly where algorithms become our superpower.
You see, at its heart, that whole plagiarism problem is really just about finding a specific sequence of characters, a string, inside a much larger pile of text. So the fundamental tool we're going to need for this is something called a string matching algorithm. Let's take a look at what that actually means.
Okay, so here's the key thing you got to remember. We have a pattern, that's our suspected copied sentence, and we have a text, that's our giant collection of a million essays. The whole goal is to find every single place where that pattern pops up in the text. This is the core task we have to solve, and believe me, we need to solve it efficiently.
So, how do we actually do this? Well, the first idea, what we call the naive approach, is to just slide our pattern over the text, one character at a time, and check if it matches. It's simple, for sure, but it is painfully slow. With huge amounts of text, it's a total non-starter. A much smarter approach is the Rabin-Karp algorithm. Instead of comparing all the letters, it compares numbers or hashes that represent the chunks of text. This is dramatically faster on average. It turns a computational nightmare into a totally manageable task. It's a genius shortcut, really.
Okay, so Rabin-Karp is clever, right? But even a genius algorithm is going to struggle searching a million essays if it's running on just one computer. It's still going to take a long time. So how do we speed things up? Well, the answer is to stop doing things one at a time and start doing a bunch of them all at once. This is the power of parallelism.
And you know what's cool? The whole idea is actually super intuitive. Just think about doing laundry. If it's just one person washing 10 shirts one after another, it's going to take forever. But if you have 5 people and 5 washing machines, you can get the job done way faster. In the world of computing, those washing machines are called threads. They let us break a big job into smaller pieces and run them at the same time on different parts of the CPU.
But, and this is a big but, just throwing more threads at a problem isn't some kind of magic bullet. We have to actually measure if it's working. Speedup basically tells us how much faster we're going. Efficiency tells us how well we're actually using those extra threads we added. And crucially, overhead is there to remind us that creating and managing all these threads has a cost. If your task is too small, all that overhead can actually make your program slower.
Now this is where things get tricky, really tricky. Parallelism introduces a classic and pretty dangerous problem. Everything is fine and dandy when each thread has its own separate work to do. But what happens when multiple threads need to look at and change the exact same piece of information at the same time?
This is what we call a race condition. Just look at this super simple piece of code. If 2 threads try to run counter++ at the exact same millisecond, one of those updates can just get lost. Think about it. Thread A reads the value, say it's 5. Before it can write back 6, thread B also reads the value 5. They both add 1 and they both write back 6. You just lost an increment, and your final count is totally wrong.
And here's the solution, and it's actually pretty elegant: synchronization. By putting a lock, also called a mutex, around that shared piece of data, we basically create a rule: only one thread gets to touch this counter at a time. So thread A grabs the lock, adds 1 to the counter, and then unlocks it. Only after it's unlocked can thread B come in, grab the lock, and do its work. This totally prevents the race and makes sure our final result is correct.
Okay, so multithreading is awesome for maxing out a single machine. But what happens when our data, our collection of a million essays, is so ridiculously massive that it doesn't even fit on one computer? Well, we have to go bigger. We have to spread the work out across an entire network of machines.
And that, my friends, brings us into the awesome world of distributed algorithms. Now, we're not just talking about threads inside one computer anymore. We're dealing with completely separate computers, which we call nodes, that have to coordinate with each other. They work together to solve one single, massive problem by passing messages back and forth over a network.
A fantastic example of this is finding what's called a minimum spanning tree in a giant graph that's spread across many different machines. The GHS algorithm solves this without any central boss telling everyone what to do. Each computer, or node, starts out as its own little island, or fragment. Then it finds the cheapest connection to another island, and they merge together. This process just keeps repeating, with these fragments getting bigger and bigger until they all form one single optimal tree. It's all done through local decisions and messages. It's so cool. Okay, deep breath. Let's put all the pieces of this puzzle together and go back to our original problem. How do we actually build that plagiarism detector to handle 1,000,000 essays? The good news is we now have all the tools we need.
Here's the game plan. First, we clean up all the text. Then, we use our good friend, the Rabin-Karp algorithm. We slide a window of, say, 10 words across every single essay, calculating a hash for each little chunk. Now that process can be massively sped up using multithreading on each machine. Then, in a distributed way, we compare all these hashes across all the different machines. When 2 hashes match, we do one final check on the actual words to make sure it wasn't just a weird coincidence. It's a beautiful combination of all 3 techniques we've talked about.
So let's just boil this all down. String matching algorithms like Rabin and Karp give us a really efficient way to do the core search. Then, multithreading lets us max out the power of each individual computer to make that search faster. And finally, distributed algorithms let us scale the entire operation across a whole fleet of computers so we can handle truly massive datasets. Each layer just builds on the last one to help us solve problems that would be completely impossible otherwise.
And that brings us to our final thought for today. We've figured out an incredible system for finding exact copied text. But the next great challenge is so much harder. What about detecting copied ideas, even when they're written in completely different words? Now that is a fascinating and really difficult challenge for the next generation of algorithms to solve. Thanks for digging into all this with me.